Hello everyone, welcome back. This is lecture 6, part 1. There will be another part. We finished with chapter 3 and we're starting with chapter 4. It is about 2 to 3 generations after Euclid, and our next protagonist will be another great mathematician of the time, Archimedes. Among other things, Archimedes did a lot of work with a circle. He wrote around 225 BC. He wrote a short book titled Measurement of a Circle, a masterpiece rather. And we shall talk about this classical work in this lecture, part 1 and part 2. The great theorem that he proved and we will talk about is determining the area of the circle. So before we talk about his great theorem, some preliminaries first, which were known before the Archimedes time. So the following are the facts that are known, as I said, before his time. Some notations first. So by the letter C, we will denote the circumference of a circle. And by the letter D, we shall denote the diameter of a circle. Okay, so before he actually arrived in the scene, the following fact was known. If you have any two circles with any two circumferences and different diameters as well, the following is true. So known facts. The ratio of circumference of a circle with its diameter is the same as the ratio of the circumference of the other circle with its diameter. So no matter what the circumference and diameter of the circle is, this ratio is always a constant, no matter what size of a circle you're talking about. So in modern mathematics, this ratio is defined as the number pi. So modern pi. So this is a constant. Okay. So if no matter what your circumference is, the ratio of circumference over diameter, if it is equal to this number pi, then this implies that the circumference is actually pi times the diameter, and since the diameter is 2 times the radius, this is our modern formula 2 pi r for the circumference of a circle. Okay, also we mentioned this before, it is in the later books of elements, the 12th book if I'm not mistaken, it was also proved by Euclid that, so this is another known fact. So let me say here known facts. If I have two circles, one with area 1 and one with diameter 1, and another one with area 2 and diameter 2, the ratio of the area over the square of diameter, no matter what the circle is always the same. So this is also a constant. So let's call this constant K. Let's call this constant K. Now, do pi and K actually relate? Is there a connection between the one-dimensional constant pi? I'm saying one-dimensional because pi concerns the circumference of the circle, and that's just a line, versus this constant that has to do with the area, which is a two-dimensional concept. So how these two constants, one-dimensional and two-dimensional constants, are actually related, if they are related at all. It is Archimedes actually that established their connection. So we'll continue with some preliminaries, also known before Archimedes' time. So here's preliminaries. Here is a theorem that concerns the area of a polygon. All right, so the area of a regular polygon, the area, remember, well, you maybe remember, maybe don't, but last time we talked about what a regular polygon is. So the area of a regular polygon is half times the height times q, where q is the perimeter, where q is perimeter of the polygon. Okay, the proof is not very difficult. I shall give you the proof. So let some polygon of n sides be given. A regular polygon, that is. Let a polygon of n sides be given, and regular polygon. So I'm going to draw one. So for the sake of simplicity, I'm just going to, let's say, draw a hexagon. Okay. Let's say I have this regular polygon. Okay. Let's say that it has six sides in this case, but an arbitrary one will have one, and the proof is exactly the same. It doesn't really matter. So the first thing we do, we are going to draw all diameters. Let me draw all diameters. Obviously not a good picture, but let's say this is the center. So draw all diameters. I will continue. Here. So draw all diameters. So we know from before that, from elements that is, if we draw all the diameters, not only the diameters will bisect the angles, each angle of the polygon, but they also are going to bisect one another. Keep in mind, this is a regular polygon. So since this is a regular polygon, diameters will bisect one another, and angles of the polygon. This is a proven fact from before. So this diameter, for example, will bisect this angle will be equal to this angle, and this side is equal to this side, and that's the case with all three of them. Okay, so we have separated in this case the polygon into 6 triangles, and we now have separated the polygon into a collection of n congruent triangles. 6 in this case. Why are the triangles congruent? Triangles are congruent by any of the congruent schemes. For example, let's consider these two. This angle is equal to this angle. The side is this side is common. This side is equal to this side. This angle is equal to this angle. So you have at least 2 of the congruent schemes that actually work here. It's a very nice construction. So it's not very difficult to see why these triangles are actually congruent to one another. Again, triangles are congruent because diameters bisect each other, and angles, and the polygon is regular. Okay. So let me denote here the height for each triangle, that it would be the same. So let's say the sides are all of length A, and the height would be H, and it would be the same for absolutely all 6 triangles. So each triangle has area. What would be the area of the triangle? Half H, the height, times the base, times little a. And there are n of those. And there are n of those. So area of this polygon is comprised of the areas of these 6 triangles, or n triangles. So let's see, area POL, that stands for the area of the polygon, is equal to the sum of areas of n triangles. Okay. In this case, we should have 1/2 HA plus 1/2 HA plus 1/2 HA n times. This would be n times, since we have n triangles. And if I factor out h over 2 here, 1/2 h, then I will have a plus a plus a n times. N times. Well, a plus a plus a n times, a plus a plus a plus a plus a plus a, 6 times in this case, it gives me the perimeter of the polygon. So n times a is nothing other than the perimeter Q. So half h times q, and I'm actually done with this. Now, this is also known from the construction point of view, that if you have a circle, you can inscribe inside a circle a polygon. So let's start now with a simple case. Let's have a circle, and we are going to inscribe a square. Okay, so this is a different business now. Given a circle, we can inscribe within it a square. We can inscribe within it a square. So let me just do that. Okay. So I'm going to inscribe a square. Probably not perfect, but let's see. This is proven that it can be done. Using just a straight edge and a compass. So, okay. Here's the square. So here's my circle, and I inscribed a square. So obviously, area of the square surely is less than the area of the circle, because the square is inscribed in the circle, so it has a lesser of an area. Okay, if we bisect the sides here, by bisecting the sides of the square, we're doing nothing other than locating the sides of, if this is a square, then we are locating the sides of an octagon inscribed in the circle. So think of this as this line being cut in half and being pushed up a little bit. So if I cut the sides of the square in half, then I am locating the sides or the vertices of an octagon inside the circle. Okay. Hopefully this is visible. Okay. Almost done. So all right. So bisecting, I'm just gonna write this. By bisecting the sides of the square, we can locate the vertices of an octagon of an octagon inscribed again in the circle. Inscribed inside the circle. Okay, so again, since this octagon is inscribed in the circle, its area surely is less than the area of the circle. So area of the octagon is less than the area of the circle. So again, we bisect the sides of the octagon, and by doing so, we are locating the vertices of a regular polygon with 16 sides inscribed in the circle. So it's a bit difficult now to let's see. Okay. So the 16-agon, if you will, is the blue one. Okay. Bear with me until I finish this. Okay. Okay. So we do this again. Where is my pen? So bisect again. The sides of the octagon and locate the vertices of a 16-agon, if you will, inscribed inside the circle. Okay, so the blue one, the area of the blue one, since it is inscribed in the circle, surely is still less than the area of the circle. Now, area of the octagon is closer, so the red one is closer to the area of the circle than the square was, and the blue one, which is the 16-agon, its area, it's even closer to the area of the circle. So we continue doing this. This can actually be done indefinitely, and for absolutely any natural number n, we can keep inscribing these regular n-gons inside the circle, each time coming up with a much better approximation of the area of the circle, but not exactly area of the circle. So we get as close as we like to the area of the circle, but not quite it. So as you can see, this green, there is this green left over here. So the area of the 16-agon, it can be seen that is very close to the circle that I have drawn, but still not exactly that area. So no matter what, we keep doing this process, and And each time we do this, we get closer and closer and closer to the area of the circle. This is actually the, so regardless what n I choose, I can always, as I said a minute ago, keep inscribing a polygon, a regular polygon with that many sides inside the circle, getting closer and closer to the actual area of a circle. This is really the modern notion of limits. So this method of exhausting, drawing pictures inside the circle, there are better approximations of its area, is what we know in modern days to be the concept of a limit. So what does that mean? It means that, so let me just write here before I move on. This can be continued indefinitely. Getting closer to the area of the circle for each, or with each n gone as n becomes larger and larger. Okay, so what does that actually mean? It means that if we have any pre-assigned area from before, no matter how small, we can always construct a regular polygon inside the circle such that the difference between area of that inscribed polygon and area of the circle is smaller than this pre-assigned area that we have. That means we can make this green area here as small as we like, in a sense that if I'm given a quantity as small as I like, I can make sure that the green area here is smaller than that. That's what we mean by the pre-assigned area. Okay, so I need to write this. If we have any given pre-assigned, area, no matter how small, we can always construct a regular polygon, inscribed in a circle, for which the area of the circle minus area of the polygon is always less than our pre-assigned amount, less than the given area, given pre-assigned area. So if I told you that I have an area that is 1/200, that's a pretty small number. It means that I can always find an area, the green one in the picture, that's the difference between area of the circle and area of the blue polygon. I can always make sure that this empty space between the n-gon and the circle is always less than any small number, as small as I like. Okay? So the analogous rule also holds for circumscribed polygons. I'm probably just going to draw a picture here. So let me continue here. Analogous result or rule holds for circumscribed n-gons around circle. Okay. And analogous. Rule holds for circumscribed polygons. So if I was to draw another circle, much like I did with this, I can also circumscribe some regular n-gon such that the difference between the area of that n-gon and my circle is as small as I like, and that is the key to what we shall prove in a bit. So I can make sure that this difference, the green one here, can be made as small as we like with the same exhausting method as in here. So this will hold for circumscribed and inscribed polygons in circles. Okay, so that is the end of part 1. I'll see you, or you'll hear from me shortly.